Okay. Needs to plug in that here as well. Okay, wow. What a great conference so far, huh? We have seen amazing talks by amazing speakers, but you know what's still missing? The AI talk. Yes, since ChatGPT, every conference has to have at least one AI talk. And I get it. I mean, it was a long day. We already have a lot of things to process. So I promise. Oh, and by the way, I also do know that I am now the only one standing between you and the after-conference beer. So I promise I will try my best to make the next 30 minutes both interesting, of course, but most importantly, also fun. So who am I? Yeah, my name is Nico. I am a front-end developer from Switzerland. I am not a freelancer anymore. I work for IT, where we provide digital finance solutions. And I'm also part of the Google Developer Experts program in two categories, in web technologies and also AI and machine learning, which basically means that I spend way too much of my free time just playing around with all kinds of new web APIs, browser technologies, and so on and so forth. And I also like to talk about those things. Now, in the last couple of years, I had quite a lot of talks. Almost all of them were in English, just a handful in German, but only 2 talks I ever gave were in Berndeutsch, which is my local Swiss German dialect. And in September 2021, I had my very first talk in Berndeutsch, and luckily that was recorded, so I'm able to show you a short clip of how that went. Can I have sound? Ist im Endeffekt, wird im Endeffekt, aber im Endeffekt, schlussendlich, im Endeffekt, schlussendlich. Yeah. I mean, that's funny now, I get it, but that was a 30 minutes talk, and I managed to use the words im Endeffekt and schlussendlich of 35 times. And that was extremely annoying to me afterwards when I've seen the clip. And both words mean the same, they mean like in the end or finally. So in February 2023, my second talk in Swiss German was just around the corner, and I was looking for ways to solve that problem. I wanted to find a solution to find or to detect those words when I'm speaking. Now, there is an API called the Web Speech API, works directly in the browser, perfect API, works perfect in English and also in German, but certainly not in Swiss German. But then again, those APIs, they are just using machine learning models, right? And can't we use them directly in the browser? Well, turns out we can. There is, for example, TensorFlow. It's an open source machine learning platform which was released in 2015 by Google. The goal here is that you can use any TensorFlow model. You can train models, you can fine-tune your models. It was originally written in Python, but since 2019, there's also TensorFlow.js, so you can use TensorFlow models in the browser and also in Node.js. And one important thing about those, about any machine learning frameworks is that machine learning operations, they use quite extensive calculations, mathematical operations. And in the case of TensorFlow.js, those are outsourced into so-called TensorFlow backends. There's the CPU backend, where those calculations are happening in JavaScript directly on the CPU, which is quite slow. So there's also a WebAssembly backend, which is a bit faster. But if we want to have performant machine learning operations, we need to use the GPU. Now, there are ways to access the GPU from the browser. There's WebGL, which is this graphical abstraction layer that uses the GPU under the hood. There is a TensorFlow backend for WebGL, which is a bit faster. But the optimal way is to use a new API called WebGPU, and it's available in Chrome since 113, so a little bit over a year. And there's also available in Chrome on Android. And the idea here is that we have a standard on top of the underlying GPU APIs like the Volcom, the DX12, and the Metal. And this also allowed TensorFlow.js to create the WebGPU backend. Now that we have some basics, let's have a look at an example. By the way, my slides will be online right after the talk, so you will have all the links and all the examples there as well. What we can do here is we have this face landmark detection model. I can import that from TensorFlow. I can create a detector, and I can then pass basically any image data. In my case, it's a reference to an HTML image element. I can pass that to the estimate faces method. It will then predict an array of faces and the key points. What I can do then is I can draw a canvas on top of my image, and then for each key point, I will just draw a point onto the canvas. So I will end up having this little mesh on top of my face. Pretty simple. Let's have a look at the demo. So what I do here is I will take the current video input, I will take the current frame of the video, I will estimate the key points, I will draw the key points on the video, and then I will take the next current frame. So you see it's a bit slow. So we are at 6 frames per second, and that's because we are using the CPU backend. If we switch to WebGL, we are now at 12 frames per second, and if we now take WebGPU, we are at 32, 33 frames. So it's almost instant face recognition directly in the browser. Now, I released the application on May the 4th, which is International Star Wars Day. So my idea was to use 2 key points between my eyes to determine the size and the position of just some 2D images, 2D image masks. So I will then use Django Fett, for example. I can draw that. I can also use Darth Vader, and I have Darth Vader mask on top of my head. And I mean, of course, it's a silly application, but it works great to showcase the difference between the GPU. I mean, it's the exact same model, exact same device, exact same application, but we're just switching the CPU, the calculation, from CPU to WebGPU, and it's just pretty cool. Now, since all of that happens in JavaScript, we can not only create web applications, but we can also do things like Chrome extensions. So another idea I had was to use hand post detection, or a hand post detection model, to then control basically any website. So I can now go to nico.dev, for example, but it should work with any website. I can now activate the extension. And what you can see then is, hello. Shouldn't take that long to load. Let's try it again. I have no idea what's happening right now. Okay, something is not working.
It's the CSP preventing the content script from getting loaded.
Yeah, but I mean, it did work just a couple of minutes before, so let's try it just one more time.
Try another side.
Yeah. Let's try that. Come on. Now it's not loading. I don't know why. But the idea was that, and it should actually work, that I can have a cursor that it will find the tip of my index finger and the tip of my thumb, and it will then take the center between my fingers as the cursor, so I can then interact with the page. I can click on links and all of that. It should work. I have no idea why it doesn't work, but let's move on to the next. Because the thing I wanted to solve is I wanted to detect words when I'm speaking, right? And well, words are not images, except when they are. Because basically any audio can be converted into a spectrogram, and now with those spectrograms we can actually train machine learning models to look for the same spectrogram in a longer or in a given talk. There is a TensorFlow model called speech commands. By default, it will just look for a set of default words like 0, 1, 2, 3, and so on and so forth. It will then give scores of how likely it was that this word appeared in the audio that it recorded. Of course, my Swiss German words are not in that list, so I had to train my own model. And there is a tool called Teachable Machine that helps you to do exactly that. So what you see there on the right-hand side is I think it's 1 hour of me just talking as a background noise class. Then I have 50 times me saying the word schlussendlich, and I have 70 times me saying the word im Endeffekt, and I can then train everything directly in the browser, so no data will leave the client at any point, and it will return a model.json and a metadata.json. I can pass those two files to this recognizer function, and it will now listen for my words. Now, since my slides are running in the browser, I was able to create a little slides extension, and I can now start the extension, and it will now listen in the background for everything I say, and whenever I say im Endeffekt, okay, it will trigger this buzzer, and I actually did use this extension in my second talk in Swiss German, and it was quite funny because yes, I did say the words from time to time, but I was very cautious because you don't want to have a buzzer going off every minute in the end. Now, that's cool. I mean, we have machine learning, we can use that in the browser, but in the end, all those models, they are just pattern recognition. And pattern recognition is just so 2019. Nowadays, it's all about generative AI. It's about LLMs, which begs the question, can we run LLMs in the browser? We have WebAssembly, we have WebGPU, so we have all the tools that we need. So the real question should be, what does it actually take to run LLMs in the browser? What problems do we need to solve to get there? Now, the way most of us use LLMs right now is basically like this. You will have an input string, you will send the input string to some LLM cloud provider, it will return an answer, and we're good. But when we want to use that directly in the browser on device, we need to dig a little bit deeper into what is happening inside this white box. First of all, machine learning models, they don't work with strings. They need numerical input, and they will also provide numerical output back. So we need to have a thing called a tokenizer. The tokenizer will split up our string into separate tokens, which are parts of words or words, and it will then convert those to their numerical representation. On the other end, we will get an array of just numbers back. We will then map those numbers to their tokens, we will concatenate those tokens, and we then have our output string. That's cool. But between that, there's some magic going on. And if there's one thing you can take home from that talk, it's that machine learning models, they don't work with, there is no magic in machine learning. Machine learning models, all comes down to basically just math, numbers, and artificial neural networks. And of course, the artificial neural network for an LLM is way more complex than that, but in the end, we have neurons, we have layers of neurons, and we have weights, the connections between those neurons. And in the case of an LLM, we can split it up into two parts. We have the architecture, we have the runtime, which basically defines how those calculations are going through the artificial neural network. And we do have the weights. And the weights are basically the result of the training process, and they are also the reason why those LLMs are as big as they are. Because if we take the Llama 2, for example, that is a 70 billion parameter LLM. It means you have 70 billion weights, which are just numbers that we have to store somehow. And if we use 16-bit floats, we will end up having around 140 gigabytes of just numbers that we need to store and process. And that's just way too much for the browser. There are smaller LLMs. There's, for example, the Gemma 2B, which is an open source LLM by Google. It's a 2 billion parameter LLM. Those parameters are stored in 32-bit floats, so we'll end up having around 30 gigabytes. Still a lot. But then there's also a process called quantization. And with quantization, instead of using 16 or 32-bit floats, we will use only 4 bits to store one number. And with that, we are down to just 1.8 gigabytes of numbers that we need to store. It's still a lot, I get that, but it is doable by the browser. On the architecture side, there are multiple projects that try to bring those architectures to the web. There is Keras, which is used by TensorFlow and MediaPipe. There is the Onyx runtime, which is used by TensorFlow.js and Transformers.js. And Transformers.js is another amazing web AI tool that we just don't have the time to look into right now. And there is the Apache TVM, which is an open source community that works on the machine learning compile stack. And that's also the tool that I use to compile models down to basically a WebAssembly file that then uses WebGPU under the hood. The weights are stored in those files, around 30 megabytes per file. So in the end, we end up having the tokenizer, the WebAssembly file, and we have the weights that we can then use in the browser. There's also a library that helps us to do that. It's called WebLLM. It's by the same people who also build the machine learning compile stack. With this library, we can create an engine. In my case, I wanted to have the Gemma 2b model. So I have the ID as Nico's Gemma 2b. I will then extend the model list with my new model with a URL to the weights and also a URL to the library. And I can then create a new conversation using a pretty simple API. So I can pass a system prompt, I can pass a user prompt, which is just my question, and I will then get the message as the full reply. So how does that look in the end? I have, it was already a couple of years ago, I created a tool called MDEdit. And the idea here was to showcase some of the modern progressive web app features for desktop applications like the File System Access API, the File Handling API, and so on and so forth. But of course, in the age of AI, I also had to add some AI features. So what we can do is you can create a new Markdown file. We then have the settings panel. So you have different models for different tasks. So you have models for translations, models for speech to text, so to transpile spoken words into text. And I also have a model for text generation. Here's the Gemma 2b. So what I can do then is I can basically use the model to say what is a GPU. Oops. There we go. And it will explain what a GPU is. Now, the really cool thing is just how fast everything is. If you look at the stats, we can see that to analyze, to understand the input, it can do that at 130 tokens per second. And to then generate the output, it can do that at 36 tokens per second. So that's just so fast, and everything happens directly in the browser on the device. We can also interact with it, of course. So we can say, let's take this as a context, and we can say, explain this. I'm 12. And it will generate a new text, and it tries to explain the same thing to me like I'm 12 years old. So that's pretty cool, again, happening directly in the browser. But now, all of those LLMs have one big problem. They're pretty bad at knowing whether they are telling the truth or they're just making something up. I mean, if I ask the LLM what a GPU is, it's very likely that I get a reasonable result because information about GPUs has already been in the training data. But if I am more specific, if I ask, for example, whether my health insurance plan covers glasses, then it gets tricky. Because in the very best case scenario, it will just tell me that it doesn't know because it has no information about my health insurance plan. In the worst case scenario, it will just make something up that sounds about right. And that's worse, that's bad. Now the solution to that is called, or a solution to that problem is called RAG, which stands for Retrieval Augmented Generation. And the idea here is that instead of just sending the question to the LLM, we will send the question together with basically the context to answer that question. Now, there are already solutions. Basically, any cloud provider has solutions, RAG solutions. But then again, do we really want to send sensitive information like our health insurance plan to some LLM cloud provider? I don't think so. Therefore, I created Ask My PDF. And Ask My PDF does exactly that. So it is a RAG solution that works directly in the browser. Let's open it up. Do you remember this document here? That was the long document that Ilian used in his talk, but he didn't want to show it because there's just too much information. So I thought it would be a great experiment to use that. So let's have the Web MIDI API documentation. It will now parse the whole PDF, and we can now ask, for example, how can I send a message to a MIDI port? Let's see. Okay. It does answer the question, which is cool, but it also provides the sources that it uses to generate the answer. So we can see that there's actually a source that it relies on, this here. There's another source that it uses, which is not that useful, but there are enough sources that it uses to answer the question to have a meaningful result. Now, how does it work under the hood? And I will make this really quick. Basically, I will parse the PDF sentence by sentence, and I will store each sentence in a little database. Now, when I ask the question, I will look in the database which of those sentences most likely answer my question. The classic way of doing that would be just to look for some words. If I have a word in the question and the same word in the sentence as well, that would be a match. But it's not very reliable. A better way is to use so-called vector embeddings. That means we use a machine learning model that was trained for semantic similarity, and we will convert each sentence to a multidimensional vector space. So we have this vector space of sentences. And then I will convert the question to the same vector space, and I will then look for the sentences that are closest to that question, so I know that those sentences are similar to the question, and I will use them to answer the prompt, or to generate the prompt in the end. And the prompt that it uses in the end is like this. So you will have some instructions. I will have all the entries that I use in the from the database, and I have the question. And what I think is super cool is just how fast everything is. I can parse the PDF in 170 milliseconds. I can then vectorize all the strings in around 3 seconds. It will find the 6 matches in 32 milliseconds. And then to generate the answer, it only takes around 4.2 seconds. And everything happens directly on device. No data leaves the client at any point. And another cool thing about this RAG pattern is it also prevents hallucinations. Because if I ask, for example, why is water blue? Or let's do it differently. Let's ask the Gemma without any RAG context first. Why is water blue? Water is not blue, its color isn't transparent, the color persists, blah, blah. It seems legit, but I have no way to prove that, right? It could be right, could be wrong, I don't know. If I ask the same question in a RAG context, it will say none. Why is it none? Well, if I look at the prompt, let's say that here. If I look at the prompt, you see that I explicitly told it that if the document doesn't contain the facts to answer the question, say none. So I prevent the LLM from actually hallucinating, just making something up, by telling it what to do if it doesn't know. Okay. Now, the problem that my demos have right now is that I always have to download the whole LLM for each origin, which means that of course, in my case, I already downloaded the model, so I have those 1.4 gigabytes already stored in the, on the browser, but I need to download it for each origin on my device. There's also a project that the people who build Chrome are working on right now, which is called the built-in AI APIs. There's a prompt API, translation API, summarization API, and so on and so forth. So the idea then is that the browser would basically provide an LLM that the web application could then use to generate text. There are some pros and cons. I'm a bit skeptical because I figured out that there's actually, depending on the LLM that it uses, you need to structure your prompt in a different way. So not every prompt works best with every LLM. But that's some details. If you want to try it out, you can go to developer.chrome.com/docs/ai/built-in. They're working on it right now. I think it's super cool that they are working on a solution, and they're also super happy to get feedback from the community. So if you have any ideas what you could build with LLMs in the browser, try it out there and provide feedback. So to sum it all up, AI in the browser, are we there yet? I would say, sure we are. I've showed you the examples where we can basically generate tokens at 40, 30 frames per second. But there's a small catch. I mean, I'm using the latest MacBook Pro, which has an M3 chip, which is an amazing device for on-device AI. I also have a Windows laptop, which has an i9 chip, which is a pretty decent chip as well. But there, I'm down at around 4 tokens per second, so it's almost 10 times slower. So yes, it does work with different devices as well, but it's just not a very webby thing to require users to have specific hardware to use your web application. The future looks bright. I mean, we have seen those large llama models where we had 70 billion parameters. Now we have small on-device LLMs that have like 1.5 or 2 billion parameters, which have amazing results as well. Hardware will be more affordable. The latest MacBook Air has the M3 chip as well. Also, Windows is working together with Qualcomm to, they're working together on this Copilot Plus laptops where you have AI-optimized hardware in Windows laptops as well. Speaking about AI-optimized hardware, in the beginning I told you that the GPU would be the most performant way to do machine learning operations, and that's true for most cases. But in my phone, for example, I also have this TPU, the Tensor Processing Unit, which is an AI-optimized chip. And right now, there's no way for me to access those AI-optimized hardware. There is a proposal called the WebNN API, which means that with the API, the browser would basically decide, or let's say the operating system would decide which processing unit it would work best to calculate machine learning operations on a specific device. So that's there as well. And last but not least, we should see AI as a progressive enhancement, which means that right now we see a lot of like AI applications where AI is the sole purpose of having those applications. I think once the dust settles, we will see more like normal customer applications that use AI for specific tasks. If we take MD-Edit, for example, it's a Markdown editor. You can use it as a Markdown editor on any device, in any browser. It works. If you want to, you can download an LLM that helps you writing text. So it's a progressive enhancement. You can enhance your UX by using an LLM, but you don't have to. On the other hand, there are a lot of upsides. First of all, when you have AI in the browser, it means we can just send the URL to our friends. They can try it out. They can play around with it. They don't need to install anything. It's highly interactive, so we don't have to make the turnaround to a server. So we can have things like 30 frames per second image recognition directly in the browser. Data stays on the client. So it's privacy preserving by default. We don't have to justify why we are sending any data to any cloud provider or storing it on our own servers. It all stays directly on the client. And it scales indefinitely, which means that even if every one of you go to my projects and you'll try it out and you will play around with it, I won't end up having a huge OpenAI bill because everyone brings their own processing power. So that being said, Web AI is definitely here to stay, and I really hope that I could inspire some of you to try it out, work with AI in the browser on your device, and start building cool stuff. So thank you very much for your attention. My slides, yeah. Thank you. So my slides are there behind the QR code. If you have questions, you can ask me in the Discord channel. You can also, I will stay around for the rest of the conference, and you can hit me up on LinkedIn and Twitter. Basically, those are the platforms that I try to be as active as possible. And yeah, thank you so much, and have a nice rest of the conference.